Alright, here is 10.3 parametric equations again and continued. So this is like number 45 in your book. So here we go. We're given the parameters and given our x and y parameters, and we are given an interval of what this is over, and we are tasked with finding an integral that will provide the surface area. Okay, so let me pause a second. Okay, so you have in your book, you have the equations for arc length. Okay, so here's the equation for arc length, looking at this in parametric form. Okay, so you have the integral from the interval. Those are two words that don't go well together very fast. Integral over the interval, AB, and then we need to take the derivative dx dt squared plus dy dt squared, or they wrote it in another form right next to it. The derivative function, first derivative with respect to t, plus squared, plus the derivative of the second with respect to t squared. Okay, and then dt on the end there. Okay, not under the radical. See the little eraser mark. Okay, so pretty easy here. We have to take the first derivative of this one. Okay, so looking at that, I'm going to rewrite it a little bit. I'm going to put brackets to, I'm going to go ahead and finish that out because of time. Okay, so taking the first derivative of this, negative, I rewrote it, so negative 2t plus 2, quantity squared, first derivative of this, multiply by this, the front side becomes 3, subtract 1 from this, and then we get that. This should be old hat for you guys. And then carry out the squaring of the terms, simplifying terms, booyah, we get that. We didn't have to take the integral. That looks like a little bit more challenging one because it's not like we're raising each part to 1/2, so this is going to be a little bit more challenging to do that. But that's all they tasked us with it to do, so we're going to move on to the next one, which we are going to take the integral of. So let me set that one up. Okay, so this is like number 50 in your book. So example number 2, we've given two more parameters, x equals t squared and y equals 2t over the interval 0 to 2. Alright, and so they ask us again for the arc length, but this time we actually want the value of the arc length. Okay, so using the same formula up above, I want to take the derivative of this, so 2t squared plus 2 squared. Alright, and then we work that out. A little bit easier integral here. I'm going to go ahead and work that out. Alright, show you the work here in a second. Okay, so now we have this going on. We squared these terms. Okay, again, taking the first derivative of this one, first derivative of this one squared. Then we're left with this. We could factor out a 4 out of this, and then take the square root of 4. So pulling the 2 out front, we're left with this. We should recognize that this is a u squared plus a squared. All right, so I'll pause there, and that should be one of our integrals using arcs. So okay, so boom, this is a lot going on here, but let's go back to where we left off. So this is u equals t and a equals 1. This was from number 26 of your appendix B, back in the back of your book. This one's a right big one. Okay, so this, boom, and we're like, what? Okay, that one's a very difficult one to memorize. So obviously you don't have to on this one, but this one's a little trick on this one. So we've got this going on. Plug and chug now. Put this in. We don't need plus c because we're looking for the interval over from 0 to 2. Calculating all these parts back, plugging in the 0 and 2 and subtracting, we get 2 radical 5 plus ln of, I'm not going to show all the work of working all that. You know how to plug in 2 first and then subtract from plugging in a 0. Okay, so then this is going to be approximately 5.916 is the value of, so again we were looking for the arc length of these parameters from 0 to 2, and there it is. Okay, that's the arc length. Okay. Alright, let me pause. Alright, so what did we do? So we put this in here. Again, what were we looking for? Window, we wanted an interval from 0 to 2. Go ahead and hit graph, and then trace. Is that? I think from my view it looks really bright, so I'm going to move it over. So basically we wanted the arc length of this. We wanted this length of this curve. That's what this formula allows us to do, is find the length of this curve. Okay? All right. Okay, so this next problem is dealing with surface area. The book uses S, and I don't like using S. I use SA because S is for arc length, distance, and I like using SA because it's area. So we want to use, when we get our units, if we have units, it's unit squared. Great place to look is page 482 and page 43. We didn't cover this section, but I'm going to talk about it. But this is a great, I mean, the pictures in the book do a lot better than my physical drawings here. So take a look at these. All right, so I've got a new equation going on here, but if you see, this looks very, very, very similar to something we just did. Okay, so that's going to be, I'm going to do the math first, and then we'll work a problem and show like what's going on here. Okay, so we are interested in finding, we want to find the surface area of some shape over this interval, okay, and that has been rotated or revolving around the x-axis. So it would be revolving around the x-axis. Okay, so if you had a straight line here, it would be revolving around the x-axis. Okay, kind of like putting something on a lathe. If you've never heard of a lathe, it's like the machine that spins, and you can like cut it, or a machine like if you wanted to make a steel rod and it's spinning, that's a lathe. And you can like cut it and smooth it out and stuff like that. So, all right, let's get started. I'll leapfrog here. Okay, so doing all the math here. Again, this was revolved around the x-axis. Yes. Double check there. This is revolved around the x-axis. And so we need to take 4t, okay, f of t goes there. If you look at the equation, there's two equations in your book, there's f of t and then g of t. Depends on which, if it's revolved around the x-axis. This one's going to be revolved around the x-axis, okay? And so we've got, this is easy derivative 4, easy derivative 1, working on that out, pulled out everything. We've got radical 17, pulled the 4 out. We've got all this thing. Easy integral, interval and integral today. So carrying that out, and then we have 207.2 units squared, or you can keep it in terms of pi. Okay, so graphing this here. All right, come on, brighten up. So that's our equation here. Looks like that. Okay, a little bit of glare going on there. Okay, so imagine this being rotated around the x-axis. Okay. Kind of think of it maybe being so actually I'll just draw. So imagine that if I were to rotate this along the x-axis here. Okay. I know it's not the best here, but it kind of maybe a lampshade or something lying outside. So the surface area that we want is all of this, and then of course on the back side. So that's what's going on here. That's what we calculated here. This was our original curve, and then we rotated around the x-axis. Okay. There you go. All right, we're going to move on to one more. Okay, so this next one is, I think, like number 69 in your book, I think, but we want the surface area, okay, of the parameter of x equals 4 cosine theta and y equals 4 sine theta. This is going to be rotated around the y-axis. So rotation around y-axis. Okay, rotation. So if it would be this way, okay, around the y-axis, rotating around the y-axis. Okay, so interval 0 to pi over 2. All right, so theta, we're using the variable theta instead of t this time, and so dx d theta is negative 4 sine theta, dy d theta is 4 cosine theta. Okay, this time, since it's rotating around the y-axis, we're going to use g of t, okay, or we're going to use the y. Okay, we can use the y to multiply by. Okay, Well, again, go look at the page 726. I did goof, and of course now I'm 10 minutes in and I don't feel like recording the whole thing. So I notice how I use 4t. Okay, so that if we go in f of t and g of t, if you look at your book, f of t and g of t, if it's rotated around the x-axis, you use g of t, which is y. All right, I did not. I used f of t. I used x. If rotation around the y-axis, use f of t or x. Okay, so taking that same idea, this line going out, and then drawing a symmetric line out this way. This is like a lampshade that's not as tall, or maybe like a cap or something, like a strange looking cap. But this one is bigger. It comes out longer out this way, and so that's the surface area. So so that would be the equation for, or the idea, the picture of this one. Okay, I did mess up. So again, think about being this rotation around the x-axis, you use y. You're multiplying by y. Okay, think that maybe. So if we think about it this way, like surface area, if you were to get like a cylinder, okay, if you open up like a can, you cut it open, it becomes a rectangle. I'm drawing this really light here. It's going to be the area of the base, okay. It's going to be the length of the base, so circumference multiplied by the height here. So essentially, we're multiplying by the length of this curve, which is this guy, okay. Then we're multiplying by f of t, okay. So in this case, it would be the y distance, but then over the integral 0 to pi. So that will allow us to rotate around. Okay, if that makes sense or not, yeah. Look at the book. It has very good pictures, better pictures than I can draw. So especially going back to these pages here. Let me finish the last one. Okay, I already have it. The reason I didn't feel like redoing it is I already had set this one up down below. So this one is going to be rotation around the y-axis. Okay, and I can tell because I use, remember, rotation around the y-axis, it says use f of t or x. So I've already used x, okay, or f of t right here, or in this case, f of theta. Alright, I've got the derivative of the first squared plus the derivative of the second squared. I'm going to carry that out. Okay, so again, for cosine here, we're multiplying by f of t. Carry this out. Ooh, this is nice. I like this. I can factor out a 16. Okay. Sine squared theta plus cosine squared theta. You know that's fundamental. One we learned, that's 1. So that's fantastic. So taking the square root of 16 out is 4. Taking this 4 out here, I have 4 times 4. I'm going to take all that out. 4 times 4 times 2. So now that's 32 pi. Left with cosine theta. Carry this over, taking the integral of cosine. So there we go. The final answer to this one, plugging this in, that's 1 there. So the final answer is 32 pi is the surface area of the region from 0 to pi over 2. Okay, let me put this in my calculator and draw a sketch here. Okay, so again, I changed the parameters, did zoom trig, and then I had changed the y to fit it a little bit better. So and then 0 to pi over 2. So pi over 2 is right up here, and here's our curve. Now imagine taking this and then rotating it around the y-axis. Okay, you can kind of think about this forming right here, taking this curve and then we rotate it all the way around the y-axis, and it basically makes this a hemisphere, or in this case, you know, or if we were to make a sphere, or a hemisphere, yeah, is what I'm looking for. Alright, so let me pause right there real quick. So we found the answer earlier to be 32 pi. Surface area of a sphere is 4 pi r squared. Hemisphere would be 1/2 the surface area of a sphere. So we look at that, your calculator, the radius of this curve is 4. And so here the math is 4 pi times 4 squared divided by 2 turns out to be 32 pi. So I thought that was rather cool. Okay, that's my 15 minutes, and y'all have a great day, and talk to you later.